example on this slide here, where you can really see the limit comparison test shine. So let's see if we can, I don't know, come to this first with some intuition, because in order to even use either of the comparison tests, we need to have a good idea of what to compare it to already, which takes some work even just to think about. So I'd like you to do that for a second. Just stare at this somewhat complicated expression and think with me, what would your guess be? And we'll write it in our thought bubble, the things we're thinking. What happened there? So tell me what you see. So far, B on the warm-up here is, I think I like what this says now. Thank you, others. Any thoughts on this one as you look at this? What's the role of the negative one there, the minus one? What part does it play? When n grows large. Yeah. It doesn't really. Right? Okay, so with that in mind, head back to the drawing table here. If you ignore the minus one, then can you resolve that expression? Does it look familiar then? You want to say something, Sean?
There you go. The wording converts to the power on the denominator is greater than the power.
Well, that's an interesting, yeah, I haven't actually even thought about what the two powers are yet. So let's think about that. What is the power in the numerator and in the denominator?
N to the 1 over N to the 1 5.
Or yeah, 3/2, whatever you like. So yeah, that's a good question. You hear what his claim is. He says that if the power on the bottom is bigger, then it converges. What say you to that? The most problematic word in that sentence, I think, is it. What does he really mean? Careful. I mean, the terms, I agree the terms do go to 0. But we have to be very careful about the series. Is that what's required, that the degree be lower on in the denominator? Let's do one more rewrite on this. What is this equal to? 1 over n to the 0.5, right? Okay, so this is like 1 over root n, right? Okay, all right. Well, I think we're going to be helpful here. Don't worry. Stay with us. So what do you want to say something now that we see this? If this really acts like this, then this is one we've talked about a lot, isn't it? What does this one do? I think this, if I have an intuition, if I have a hunch, if I have at least a feeling about this, it's that this diverges. And now we're going to write it up in a second more formally with a sentence and a period and all that. But I think we've already established that, like, if we ignore the -1, it's kind of playing fast and loose. But it does feel like it took some work to get us to think this way. But it does feel like 1 over root n, and I think that's what we're going to choose to compare it to. We'll use the limit comparison test with that.
Mr. Chase, how did you go from n to the first over n to 1.5 to 1 over n to 0.5?
Someone take that question. In the thought bubble, how do we do the algebra? And Anya? Is that sufficient, Cameron?
No, but wouldn't, if you divide, you have to divide by n over n to make it work.
That didn't go in the direction of simpler though, but that is true. Can someone else help with the algebra in the thought bubble? Maybe it's not as obvious as some of us first said it was. So, is some, huh? Leo? Oh no. Anyone else willing to say it your way?
You're dividing. You're not multiplying.
Oh, because then you can divide n squared over n2 from 1. Whatever. You can just divide it, never mind. You can make n to the base of 1 and divide by n to 1.5 and just work that.
Yeah. There are a number of ways to explain it. Yeah, but n to the 1.5 is n to the first times n to the 0.5. You know, so those cancel out. Or you could think about subtracting exponents, the rule that you have about subtracting exponents when you divide. All right, let's write it out nicely here. This is our intuition, but let's actually kind of formalize this now. Okay, so here we go. Since 1 over root n, or n to the 1/2, n goes from 2 to infinity, diverges. This isn't, but this is a p-series, right, with equals 1/2, which is less than or equal to 1. So this diverges. And, furthermore, now here comes, this is a little bit of the messy algebra. We haven't actually waded into this yet, but let's actually see if we can get this to come out to be a constant. When we stack these two, 1 over n to the 1/2, divided by the thing we have, n over square root of n cubed minus 1. Let's hope that we get a constant ratio. Isn't that what we want? That these two series always stay in proportion to one another? If we claim they grow at the same rate, that's what we're claiming. Yeah, go ahead, Franklin. Does the rule only apply to the numerator?
No, does the rule only apply to the numerator of 1?
You mean when this limit comes out to 1, you mean?
No, like when the value on the numerator.
You mean the p-series test? Is that what you're talking about?
Yeah.
Yeah. Technically, yes. But it's easy to just factor. If there really is a different number up top, then you can just factor it out. And then you have some number times the p-series, which either clearly converges or diverges if the series does. So whatever it does, times that number, right? By properties of summation. Yeah, Cheyenne. Huh? Oh, you're desperate. Okay, go ahead. Yeah. I'm just doing a little bit of, fraction action there. Is that okay? Yeah, Steve. Yeah, if p is greater than 1, strictly greater than 1, it converges. Yeah, the inequality, the or equal to thing, you have to think hard about. But I think I said it right, though. Yeah.
I'm still kind of confused on the limit comparison test. So, can you just explain to me that sentence? I understand how the 1/2 is less than equal to 1, but I just don't understand that sentence.
This part?
Yeah.
Well, it's probably because we're not quite done with it, but we're in order for us to make a claim that this has the same limiting behavior as this, that is, they grow at the same rate. That is, they act the same way. If this converges, this does. If this diverges, right? If they grow at the same rate, then one way to assert that they grow at the same rate is by saying that, if you were to look at the terms themselves and take the ratio between the terms of this series and this series, you would get a constant in the limit. Like they wouldn't grow apart from each other, right? They'd always be in exactly the same ratio to one another or something. So that's what we're doing here.
That one to basically the same thing.
Yeah. Then.
Without the -1.
Well, no. Okay. In this particular case, that's true. But here, this is I'm comparing a known to an unknown, right? So we don't know about this guy. This one we do know. So if we get a constant, what that says is that these tie. And if this diverges, well, then this must too. If they tie, if they grow at the same rate and this diverges, well, then that must mean this diverges too. So let's finish the work here. Yeah, Sophie. So, like I said, so the reason that we're stacking them is that, for example, this goes even back to our rational functions unit. Like, you know that if you have a cubic and a cubic, that they kind of tie. They grow at the same rate. up to some constant, right? And then you just take the constant ratio of the two. If you have a cubic on top of a cubic, right? What you're doing is comparing, in what sense do they grow at this, does a cubic and another cubic grow at the same rate? Well, when you stack them and you get a ratio that's a constant number, which you do, then we would say they grow at the same rate, right? In fact, that would be true for, huh? So we're saying if we get a constant here when we stack these two, then we'll know that these two functions have the same limiting behavior, right? That is, like you would say that, how else can I explain that? Yeah, I mean, I'm trying to give, like, let's try that cubic example. I mean, I think you would say that this has the same end behavior as x cubed because the limit as x grows large is 2, right? Right, so these polynomials have like the same end behavior model. All I'm saying is, so these, what you're claiming when you do that is you're like comparing these two different functions that grow at different rates, or do they? Actually, they grow at the same rate, don't they? But if you put a 4 down here, then suddenly you have two functions that don't grow at the same rate, do you? Right? This one grows faster. So what do you get? No. Well, yeah. I mean, 1 over x or something, 2 over x, kind of. But 0, right? You remember this discussion from earlier in the year? Or here, 2. But if this was a cubic and a cubic, then we get a constant. Whether it be 2 or some other constant, we get a constant. So that tells me that they grow at the same rate. They tie. If this one is going somewhere, this is going to that place too, at the same speed. At the same speed, even. But if I get infinity or 0, then that tells me one of them won. Right? They didn't tie in the end. Yeah. Cassie.
Okay, I understand that if one over the other is a constant ratio, it means
Yeah.
they're like, they kind of move together.
Yeah.
One divided
Yeah.
the other divided. But I don't understand the notation, because it looks to me like the limit as n approaches infinity is the ratio?
No. This is the limit of this expression. We're asking. What we're asking. This is a question still.
Okay.
What is the limit as n grows large when you stack these? Just like we did over there. That's the question. And we're about to tell you what the answer is here in a second, right?
Okay.
This is the question, but we don't have an answer yet. We're not saying that the limit is this. No.
Okay.
We're saying we're asking, what is the limit as n grows large for this expression? In this expression, what happens if you plug in really big n values? Is the question. Yeah, Cameron. No. In some people write up the limit comparison test and express it in different ways, that theorem, but we'll stick with the way it's written there. All right, let's finish the algebra, and then maybe that will help answer some questions here. Downstairs, we now have n cubed, the square root of n cubed again, right? So the algebra is like a little messy here, but I think we can handle it. We could maybe express that as 1 square root. And now I think it's clear that as n grows large, what happens to the radicands? I mean the thing inside the radicand. What happens to that? It tends to what?
Go towards 1.
Yeah, and then the limit of the overall expression goes to the square root of that, which is 1. I think we've made it clear. If it wasn't clear here, I think it's now clear as we change this algebra, the form of this expression to this. It's becoming clearer and clearer, and we could even go further if you like, that the limit as n goes to infinity is 1. Okay? So what does that tell us? Again, that tells us that as you put numbers into this and as you put numbers into this, this confirms our intuition that these do have always the same ratio. In fact, the ratio is very simple here. It's 1. These are in ratio. As you put really large n values, if you plug 1,000,000 into this and 1,000,000 into this, the ratio between those two outputs is basically 1, right? They're basically the same result, is what that's saying. Which is not 0 or infinity. So this series must diverge also by the limit comparison test is how we want to finish that, right? But again, it's important that we get a constant. If we get, just to be clear, if you pick because this is a little bit tricky at the front of this problem, right? To even think of what it is we're going to compare it to. If you pick the wrong thing to compare it to, like life is not over, right? What will happen? You'll do this, and at the end you'll get 0, or you'll get infinity, and you'll be like, oh, shucks, I just need to try a different series. Then you could try another series and see if you get a constant, right? It's inconclusive. This test is inconclusive if you get 0 or infinity, right? But if you get a constant that says, both of these must grow at the same rate. If this diverges, which it does, this must too, right? Yeah.
When we're doing this for the test, we have to show all the steps in the bottom and the top, and do we have to write our
Yeah.
explanation?
Yeah.
It's complicated.
Yeah. Doesn't have to be those exact words, but you should write something meaningful that includes those elements. All right, we do need to move on here. Quick question, Matthew.
Say why 1 over n plus 1 half that diverges.
I kind of did in parentheses here. The point is, you should say that the reason you know that is because of the P series. But I think that's enough explanation, something like that. Yeah. Can we hold? Do you mind? I didn't mean to spend class redoing the limit comparison test again. I'd like to say something about the ratio test, if that's okay. So, and then we'll return to questions if we have them on limit comparison test. All right. So then I need you to be able to do the homework tonight too, right? That's the point here too. Okay. This is the last one, so you don't need to write this down exactly if you don't want. It's written in exact form on your blue sheet number 6, right? The ratio test. Again, just like the limit comparison test, this is a very loaded set of symbols here. an plus 1 over an. That's very small and cute, but what we mean there by an plus 1 is take your series, your explicit rule for your series, and plug in n plus 1. And if you have a very complicated rule, well then this ends up being a very complicated expression with your series explicit rule with n plus 1s instead of n's. Over your series with n just plugged in, which is normally probably how it appears already. And what does that give you? Forget the limit for a second. What does that give you if you just think about that expression, a sub n plus 1 divided by a sub n? Well, if n is, say, 100, for any series, what that gives us is the ratio between the 101st term and the 100th term. Great. So, and same if you plug in, so what you have with this stacked expression now, these are not two different series. This is the next term to the current term, always. So if you plug in 1,000,000, you get the ratio between the 1,000,001st term and the 1,000,000th term. That's interesting. What happens if this is a geometric series? What ratio do you get? You always get, in fact, no matter what you do, whether you plug in 100 to this expression or 1,000,000, you'll always get, not just approximately, but you'll always get the same number, in fact, right? Because that's what the definition of a geometric series is. The ratio test says, though, that if you have any series, even if it's not geometric, that out at infinity, if you get a number, right, even if it's not true, that as you go from one term to the next term, you multiply by 1/3 or something, if it's approximately true, and that it ever more becomes more true as you go out to infinity, that, hey, to get from one term to the next term, you multiply by about 1/3. Then guess what? It acts, even though it's not geometric, it acts like, in that case, a convergent geometric series. And in fact, we're even using the same notation down here, and none of this should be, all of this should be familiar down here, yes? It makes you think, oh yeah, this is just us like saying, if this happens, then it acts geometric, and if this happens, then it's a convergent, and if this happens, it's a divergent geometric series. So all the rest of this, we're kind of treating a series, even if it's not geometric, as if it is geometric, right? It's inconclusive if R comes out to be 1, though. Yeah, in absolute
So
value.
why wouldn't it just be a geometric sequence? How would there
Yeah,
be
for a geometric series, this limit is not required, right? You always get the same number. There's no need to be like, well, it's approximately a half. times, and then another times a half, the next, to get from one term to the next. It's about a half. No. If it's geometric, it is a half, or it is a third or something, right? But what we're saying is for any series, even if it's not geometric, maybe it doesn't even start out, it's like wildly not geometric. But out in infinity, if it acts geometric, then we can use basically the geometric series test, is what we're saying. So let's try that with this example here. And we'll write this out. Well, the first thing we need here is a rule, so let's get that. What's the rule? What's the rule? N over 2 to the n? All right, so good. Now already you can see that this, we can apply some of our other tests. By the nth term test, these terms do go to 0, so inconclusive, move on. This isn't geometric. It's not a p-series. None of those works. Maybe a comparison test might fit here if you are able to compare this to like the geometric series, 1 over 2 to the n or something like that. That might work. But it does say let's try the ratio test, so let's do it. Here we go. So I'm going to say, I'm going to actually compute this r value. We're going to calculate the limit of the ratio of the next term, which is n plus 1 over 2 to the n plus 1. Do you agree that that's the next term? If this currently is the current term. Notice again that if into this tower that I just formed, if you plug in like a million, what that gives you is the ratio between the million first term and the millionth term of this particular series, right? Right? In fact, you could even write the next term here is n plus 1 over 2 to the n plus 1. Right? So it's ratio of this to this. Good. Let's do the same kind of fractions action here that we've been doing. We're getting used to this kind of arrangement. So we have what? N plus 1 over 2 to the n plus 1 times, flip that thing. You see anything that can be simplified at all, algebraically? Yeah, this is a 2 to the n, and this is a 2 to the n times 2 more. Isn't that what 2 to the n plus 1 is? 2 to the n times 2. So those cancel out, leaving just a 2 behind. So someone say that again? What happened here?
You divided 2 to the n, 2 to the n plus 1, so that means like, so if you make it 2 to the n minus 1, which then becomes 2 to the 1, which becomes 3, right? Yeah.
So this is the fundamental thing we're using to get this, right? Is that 2 to the n plus 1 is 2 to the n times 2, isn't it? Rules of exponents. Right, add exponents. So then if this is 2 to the n times 2, well, the 2 to the n's cancel out, leaving just behind a 2. So, all right, now we're ready to evaluate the limit. It's what? Sure it is. Let n grow large and think about the horizontal asymptote of this parentheses here. Right? Which is less than 1. And technically we need absolute values around all these things, right? You know, we want the common ratio, or well, it's just the ratio in the limit here. So the series converges by the ratio test. Again, it should be obvious here, I think, that this is not a geometric series. But what we're saying is that out in infinity, in order to get like from the millionth term to the million first term, you basically multiply by 0.5. That's not 100% accurate, but it's very, 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 very close to being accurate, right? So if this acts out at infinity like a convergent geometric series with common ratio 0.5, well then I think it converges. It would be a mistake to go on and say what this converges to by using the infinite geometric sum formula, though. That doesn't apply here, because this isn't geometric, let's be clear. This isn't a geometric series. We're just saying out in infinity, it does act like one once you get far enough out.
How does n plus 1 over 2 to the n equal 1/2?
So as n grows large, if you plug in 1,000,000 or something, you get 1,000,000 over 2,000,000, approximately, right? Yeah.
Wait, if the series like in the beginning doesn't act like a dimensional equation, how is it possible that it's going to act like infinity?
Well, that doesn't always happen, right? It just so happens that this one does. It turns out that like 2 to the n really dominates the behavior, it turns out. Like the n, for an exponential function, like the n almost doesn't happen. All right, let me show you one more here, 2. Well, I just want you to see how this feels too. I gave you the rule on this one, so let's give this a try. So we'll even start the same way here, and we'll stack these up. And I want you to tell me what you see here. How's that gonna go? What do you get after you do all that? Yeah, what's the limit come out to be? What's R come out to be?
1.
Yeah, so what does the ratio test have to say about this particular guy? It has nothing. It has nothing to say about this one. So I wanted you to see one that comes out to be inconclusive as well.
Why do you stack
Is there, so the ratio test doesn't work here, right? Is there another test that would work here? What do you think? Forget the ratio test. If I gave this to you in your warm-up today, what would you have said? Huh? What's that? Yeah, I might compare this to 1 over n. I think this diverges. So the ratio test is not like the be-all and end-all. Some of your other tests work great too. Let's finish this worksheet. There's a back as well. And do the 3 from last night that we didn't do, okay?
You guys got so many extra days to work on it.
I think you'll do okay.
So what is it? This carefully. This is more the slant asymptote, right?
Yeah, this has a slant asymptote. You can divide it exactly. Yep.
Also, are we having a festival of knowledge this semester?
I think we're not gonna have a festival of knowledge. We're gonna do something else. I don't know. We haven't fully decided yet. We're in new territory. What's up, girls? You got a new joke for us? Thinking of it right now. Huh? Oh, you're trying to get this one. Yeah. Is this one of Lauren's ones? I don't know. They're trying to come up with, is this yours, Lauren? Yeah. They're trying to come up with the answer.
Is it like an actual pet?
Probably gonna be a pun with like a synonym of loud and
Good. Amazon?
loud.
Amazon might have some good ones.